Welcome to the third review lecture. In this lecture, we look at thermal energy flux as well as the charge flux. The thermal energy flux is or thermal heat transport is more relevant to us. However, the total energy is conserved. Thermal energy alone is not conserved. Therefore, we looked at total energy and then backed out thermal energy part of it on one side, and that's how we could write this expression. So, we also saw before attempting the equation of heat, an equation of heat energy, that heat is transferred by three major mechanisms. One is conduction due to molecular processes. The other one is convection due to movement of the medium, bulk flow. The third is radiation, which is through electromagnetic waves and so on and so forth. It can happen even in free space. First we saw the equation for conduction alone, the Fourier's law. Q equals minus K del T, okay, dt dx in one dimension or del T in three dimensions. Then alpha, the thermal diffusivity, K by rho Cp, has the same units as that of mass diffusivity as well as intrinsic viscosity mu by rho. Okay. So, mu by rho has the same units, meter squared per second. So, they are all equivalent physical quantities is what we can say for different transports. Then this table gives you the thermal energy flux when only conduction is involved. You are asked to make a copy of it and keep it as a part of your notes for these three different coordinate systems. Right. Okay. Then we had looked at the equation of energy. We didn't spend as much time with the equation of energy. However, the equation of energy the same way. Before that, let me say this. Again, you could do two approaches here. One is shell balances, the other one is derive the conservation equation, write it in a form that would be useful and use it directly for most situations. I did not explicitly show you shell balances here. I went directly to the equation approach, and that was the outline of how we got there was discussed in some detail. Then we put everything together. We got the equation of energy as dou T rho U, this is internal energy, plus half V squared. Therefore, rate of energy gain per unit volume of the control volume equals minus del dot rho V times U hat plus half V squared. This is rate of energy in per unit volume by convection minus del dot Q, rate of energy in per unit volume by conduction, plus rho V dot G, the rate of work done on the fluid per unit volume by gravitational forces, minus del dot PV, the rate of work done on the fluid per unit volume by pressure forces, minus del dot tau dot V, rate of work done on the fluid per unit volume by viscous forces, plus Q dot other, it could be metabolic, minus W dot other, okay, other shaft work and so on. Okay, other work and so on. So, that we wrote in a useful form. We looked at the double dot product, which is a scalar product between two tensors or equivalents, which also has 9 components. And then I showed you the application of course, there were tables of the energy equation, which I had asked you to make a copy of and keep as a part of your notes. Okay, I am just flashing this here. I am not going to discuss this here. Then I showed you how we discussed how you could use the equation of thermal energy to get to the temperature profile in a tissue. This was the first example. Then by cancelling the irrelevant terms, we could get to the governing equation, which we can solve in a fashion similar to what we did for laminar flow through a pipe to get a parabolic profile of non-dimensional temperature versus non-dimensional dimension, and also we looked at the rate of heat dissipation at the cylindrical surface. Then we plugged in some numbers to see that the maximum temperature is about 0.3 degrees higher, or could be about 0.3 degrees higher compared to the surface temperature. Okay. Then we saw an example with unsteady state. Right. This has been the pattern. We looked at steady state cases and then unsteady state. Unsteady state, just to give you a flavor of the complexities involved and what does unsteady state really mean, where all does it become relevant, and so on and so forth, or where you should start looking for unsteady state, okay, despite the mathematical complexity, that is. And an example was given that complicated with the complications in the mathematical part of it, and it's a very relevant situation. Okay, we looked at a microanalysis system, the time that it takes for the entire droplet to reach a certain temperature, which is necessary for a certain reaction to occur, which could be one of the key reactions in this type of processes that are relevant for that particular system. Then we looked at charge flux. Okay. We said biological engineers need to look at charge flux in some detail because the fundamental biomolecules could all be charged. Okay. Lipids are always charged, carbohydrates are many of them are charged, proteins are charged, nucleic acids are charged, and therefore we are dealing with charged particles as the fundamental units of all our systems, and therefore we need to look at charge flux is what was mentioned. And we looked at some background, we derived the charge balance equation the same way that we derived the other balance equations. Before that, the force that is experienced by a particle that is moving in an electromagnetic field is given by Lorenz's force law, F equals Q times E plus V cross mu naught H. This is we reviewed this, and then we defined charge density, charge flux, and then based on those quantities we derived the charge conservation equation. It's a rather simple derivation compared to the other things, and we could get dou rho dou t plus del dot I dash, the charge flux here, equals 0, the differential form of the charge conservation equation. Then you are introduced to the Maxwell's relations, Maxwell's equations, which are the fundamental equations for all electromagnetism. They answer these questions. The first one answers how is the electric field related to its source, the Gauss's law. Second one answers how is the magnetic field intensity related to its source, the charge flux. That results in Ampere's integral law. Then the third, Maxwell's equation, describes how are electric field and magnetic flux related. Okay. That is the Faraday's integral law. Then a comment on the net magnetic flux out of any region was given by Maxwell's fourth equation, which is also called the Gauss's integral law. Then we saw a few simplifications that make our life easier, especially when we deal with electromagnetism in biological systems, such as the differential forms, how to convert from the integral forms to the differential forms we saw by using the two theorems, the Gauss's theorem and the Stokes theorem in mathematics. And then these were the differential forms. On top of that, we said that these are fine for free space. For biological systems, you don't have free space, you have a medium, and therefore you cannot use the permittivity of free space. You'll have to use the permittivity of the medium. However, the permeability of free spaces does not change in these equations. So, the same equations that we had earlier can be used just by changing epsilon naught to epsilon. The effects that we discussed because of the presence of the medium are polarization and magnetization. Right. Then we also saw the electro quasi state approximation and the magneto quasi state approximation, which effectively delete the time variations, the time derivatives in the Maxwell's equations, and they become simpler for us to use for interactions with biological situations, biological systems, that is. So, these are the equations of relevance. We also saw that these equations can be used for any situation. We saw how you could use this to get a capacitor equation, and the lipid bilayer membrane can be viewed as a capacitor. Right? Yeah. Then we saw the Poisson equation, Laplace equation, which are useful equations for analysis. Then we saw Ohm's law as a constitutive equation. Okay, I think that's where we finished up there. And then we saw some Maxwell application of Maxwell's equations, as I just mentioned. And we also said that the fundamental equations on which EEG is based is also derived from Maxwell's equations. For that matter, anything is fundamentally derived from Maxwell's equations. Then we saw the aspects of charges in solution, 3 different important aspects related to charges in solution or ions in solution. First one was electron neutrality, the second one was charge relaxation time, and the third aspect was the Debye length, okay, the region where the electron neutrality does not hold, especially when you have a surface of when you have a charged surface in solution. Okay, these are all relevant aspects for analysis. I think this is what we saw till this chapter. We also saw that it's good to realize charge carrying biomolecules in a system do not generate an electric field because they are shielded by counter ions as a double layer counter ion cloud. However, when the electric field is applied, the double layer counter ion cloud surrounding the charged biomolecule gets disturbed, and then the charged biomolecule experiences the presence of the field and moves in response to it. Okay, we will take a break here. I think it's time. Then when we meet for the next lecture, the last review lecture, we would look at multiple driving forces being responsible for air flux or multiple fluxes, okay, predominantly air flux. That is the review of the last chapter. See you then.